We're starting a new unit on polygons, and today we're going to talk particularly about how we can classify different types of polygons. Let's start by talking about what a polygon is. A polygon is a figure in a plane with the following properties. It must be closed, so it's not just a random string of line segments, but it actually goes back to where it started. It is formed by 3 or more line segments that are called sides, and each side intersects exactly 2 sides, one at each endpoint. And lastly, each endpoint of a side is what we call a vertex of the polygon. Now, a segment that connects any 2 non-consecutive sides, so in other words, 2 sides that aren't next to each other, is what we call a diagonal. Here's an example. So we have a polygon, we would call this polygon ABCDE, and we see here AE is a side, we see C is a vertex, and we see connecting B and D, that green line is not part of the polygon, but by drawing that line, you've created a diagonal. Now there are different types of polygons. One type is what we call equilateral polygons. These are polygons that have all congruent sides. Next we have equiangular polygons, and these are polygons that have all congruent angles. Now regular polygons are both equilateral and equiangular. So when we say we have a regular triangle, a regular pentagon, that means that all the sides and all the angles in that polygon are the same. Now we say that a polygon is concave if any part of a diagonal contains points in the exterior of the polygon. So here's an example. Here's a polygon, and it has 4 sides, 4 line segments. It's closed, but we say it's concave because by connecting those 2 vertices that are not consecutive vertices, we've drawn a diagonal, and that diagonal contains points that are on the outside of the polygon. So that's what we call a concave polygon. Now we say a polygon is convex if there's no diagonal that contains points in the exterior. So here's an example of that. We can see here this has 4 sides as well, and we've drawn in actually all the possible diagonals, and none of those diagonals are on the outside of the polygon. So this is what we call a convex polygon. Okay, take a look at example 1. We're going to tell whether the figure given is a polygon, and then whether it is convex or concave. So let's look at the first one, part A. So here we see that we have all line segments. However, some of the segments intersect more than just 2 segments. So if you look at that middle line segment, we can see that intersects 4 different segments. So we would say this is not a polygon. Look at B. It looks like we have 1, 2, 3, 4, 5, 6 sides. So this looks good. They're all line segments. It looks like a polygon. Now the question is it a convex or a concave polygon? So if we were to draw all the diagonals within that polygon, all those diagonals in this case would all be inside of the polygon. So we would say this is a convex polygon. All right, looking at C, it looks like we have 3 sides here, but one of those sides is a curved line. Now, when we talk about lines in geometry, we're always talking about straight lines. So, since we don't have 3 line segments, we only have 2 line segments and 1 curved side, we would say this is not a polygon. All right, in the next one, it looks like we have all line segments, and now we just have to determine whether this is convex or concave. So drawing the diagonals, so connecting any vertices that are not next to each other, we're able to find that there are diagonals that we can draw where those points are outside of the polygon. So since there are diagonals that end up outside of the polygon, we would say that this figure is a concave polygon. All right, now let's talk about how we can classify polygons by the number of sides. So we're going to have this chart here, and we're going to list off the number of sides and what we call that polygon. So a polygon with 3 sides, we call a triangle. A polygon with 4 sides, we're going to call a quadrilateral. It's not a square, because a square is when they're all equal, but they're not necessarily all equal. So we call it a quadrilateral. If it has 5 sides, we call it a pentagon. 6 sides would be a hexagon. 7 would be a heptagon. 8, an octagon. 9 sides is a nonagon. 10 sides is a decagon, like a decade. And 12 sides is a dodecagon. Now we don't have one for 11, and we don't have names for those higher than 12 that we are going to go through in this class. But a general way that you can classify polygons is to simply say however many sides and then add gon after it. So say you have a polygon that has 14 sides. You can call it a 14gon. So n being the number of sides, you can call it an n-gon. Okay, take a look at example 2. Classify the polygon by the number of sides and tell whether the polygon is equilateral, equiangular, or regular. Explain your reasoning. Okay, so looking at the first one, this polygon here has 6 sides, so we know it's going to be a hexagon. And now we also want to look at the sides, which look like they're all congruent to each other, and the angles, which are also all congruent to each other. So, since it is both equilateral and equiangular, we can simply say it is a regular hexagon. All right, B. This polygon we see has 4 sides, so it's some sort of a quadrilateral. We see that it is not equilateral, because not all the sides are equal to each other. And it is not equiangular, because those angles are not all equal to each other either. So we can simply say that this is a quadrilateral. All right, the last one, we see this polygon here has 12 sides, so we would say this is a dodecagon. And then looking at the sides, we see all the sides are congruent to each other. However, we can see that the angles inside this polygon are not all equal. So while it looks like they all form 90-degree angles, we're always looking at the angles inside of the polygon. So notice how some of these 90-degree angles are on the outside. If you were looking at the angle on the inside, it's actually an angle of measure 270 degrees. So while this may have congruent sides, it does not have all congruent angles. So we would say it is an equilateral dodecagon. All right, example 3. The table is shaped like a regular hexagon. The expressions shown represent side lengths of the hexagonal table. Find the length of a side. Now, since you know this is a regular hexagon, you know that the measures of each of the sides must be equal to each other. Now, one side is given as 3x plus 6, and the other side is given as 4x minus 2. So to solve this, we can set those equal to each other since we know those lengths are the same. Now solving this, we end up getting x is equal to 8. Now the question is not asking us to find what x is equal to. This is asking us to find the length of one of the sides. Now it doesn't matter if you use 3x plus 6 or if you use 4x minus 2. Either way, you should end up with the same answer. We're going to substitute 8 in for x. I'm going to do it in 3x plus 6, so 3 times 8 plus 6, which is equal to 30. So the length of a side of the table is 30 inches. You'll notice that if I had plugged 8 into 4x minus 2, we would have had 4 times 8 minus 2, which would have also given us 30. All right, we're going to move on to finding angle measures in polygons. So the first theorem we're going to talk about is what we call the polygon interior angles theorem. This says that the sum of the measures of the interior angles of a polygon is equal to n minus 2 times 180. What is n? Well, n stands for the number of sides. So say here, for example, this has 6 sides, so I know that the measure of the interior angles of this polygon will be 6 minus 2, which is 4, times 180. Let's look at example 4. Find the sum of the measures of the interior angles of an octagon. So an octagon, you know, has 8 sides, and so using this theorem, we would find n minus 2 times 180, which would be 8 minus 2 times 180. Simplifying inside the parentheses, we have 6 times 180, which is equal to 1080 degrees. So the sum of the interior angles in an octagon is 1080 degrees. All right, the next one. The sum of the measures of the interior angles of a polygon is 900 degrees. Classify the polygon by the number of sides. So again, we'll use the polygon interior angles theorem, but this time we're solving for what n is. We want to know how many sides does this polygon have. So n minus 2 times 180 equals 900. Now dividing both sides by 180, and then adding 2 to both sides, we end up with n is equal to 7. So we're working with a 7-sided polygon. What is that called? That is a heptagon. All right, the last one. Find the value of x in the diagram shown. So we know that the sum of all these angles, so x plus 108 plus 121 plus 59, should equal some value. What is that value going to be? Well, since it is a 4-sided figure, it is a quadrilateral, we know that the sum of those angles must equal 4 minus 2 times 180. So 2 times 180, which is 360 degrees. So x plus 108 plus 121 plus 59 equals 360 degrees. We have x plus 288 equals 360. Subtracting 288 from both sides, we end up getting x is equal to 72. So the measure of angle x there is 72 degrees. Okay, let's talk about the exterior angles. Now, unlike interior angles, the measures of exterior angles do not depend on the number of sides. Let's try to visually imagine this. Since exterior angles go around a figure, let's say you have this picture here. You see angle 1, 2, 3, 4, and 5 that are shaded. Those are the exterior angles. Now, if we were to take away all the line segments and just look at those angle measures, you'll notice that if we put them together, much closer together, that they will equal 360 degrees. So because exterior angles go around the figure, those angle measures are always going to equal 360 degrees. It does not depend on the number of sides of the polygon. So the polygon exterior angles theorem says the sum of the measures of the exterior angles of a polygon is always 360 degrees. All right, take a look at example 7. What is the value of x in the diagram shown? So you're given all exterior angles here. So we'll go ahead and add them all up, and we know that that should sum up to 360 degrees. So x plus 2x plus 89 plus 67 is equal to 360. Simplifying the left, we have 3x plus 156 equals 360. And subtracting 156 and dividing both sides by 3, we get x is equal to 68. The correct answer is going to be B. All right, we have one last example. We have a trampoline here. It says the trampoline shown is shaped like a regular dodecagon. Find A, the measure of each interior angle, and B, the measure of each exterior angle. Let's start by determining what the sum of all the interior angles would be. So we have a dodecagon, which means this has 12 sides, so that would be 12 minus 2 times 180. That comes out to be 10 times 180, which is 1,800 degrees. Now, since you're trying to find the measure of each interior angle, how many angles are there altogether in a dodecagon? There are 12 angles altogether. So if I take this 1,800 and divide it evenly by 12, that gives me that each angle is 150 degrees. Now for the exterior angles, we know that they all sum up to 360 degrees. But we want to find the measure of each exterior angle, and since there are 12 exterior angles in a dodecagon, we take 360, divide that by 12, and that's equal to 30 degrees. So the measure of each exterior angle is 30 degrees.